Hi, in this lecture we will learn about ideal gases, their kinetic theory, phase equilibrium, and phase changes. Let's get started. So to start with some observations, first of all, for example, assume that you have a basketball and you pump air in. So the volume of the basketball is fixed. So the volume is fixed. The temperature, if you do this process slowly, the temperature will not change. It will be basically the ambient temperature or the room temperature. So this is also fixed. And the observation is that if you pump molecules inside, so if you increase the number of molecules, what happens is you also increase the pressure. So this is something that we know from daily life. If you pump air inside, so basically you're increasing N, number of molecules, the pressure increases, so it becomes, the basketball becomes harder. The second observation is, if you have a container where now the number of molecules are fixed, so if you have a container like this, and there's this piston that can go up and down, but N is fixed now, but the pressure can change. And if you fix the temperature, again, in this case, whatever you do, like pushing the piston down, if you do it really, really slowly, so the temperature will not raise, it will not change. So what happens is, the relation that you find here is, if you decrease the volume, so you push it down and the volume goes down, and in this relation, because the volume, so what you see here, the phenomenon that you see is when you decrease the volume, you look at the gauge and you see that the pressure increases. And if you write the formula for it, you would write a formula where the pressure is inversely proportional to the volume, with the volume. So as the volume goes down and you look at the gauge, the volume goes down and the pressure increases. So the relation that you have to write is, it should be like this. So the pressure and the volume should be inversely proportional. Now, the third observation is that if you have a fixed volume, so in this case, you have this gas, its volume is fixed. And if you have the fixed number of molecules, and you can see that there's some mercury in here, so water molecules or air molecules from outside cannot go in, so the number of molecules is also fixed. Now, if you heat it up, let's say you start heating this, give heat to the gas here by heating it, what you notice is, as the temperature increases, you see that this mercury rises here, mercury level. So that is raise happens because the temperature inside is increasing. So then you infer that the pressure and the temperature, they are directly proportional. So there's a linear relationship between them. So you would write an equation like this. So this part, the constant part, historically it was not known, so people made these observations, but later we will see, later in the slides, we will see that all of these lead to the ideal gas formula, which is PV and KT. Here K it's just a constant, Boltzmann constant. But historically, these were the observations. So the point here is, you can make an observation, you can make an experiment, and from the experiment, you can find the relation between the variables. These are all thermodynamic variables: pressure, temperature, they're thermodynamic variables. Okay, let's talk about pressure a little bit more. So pressure is force per unit area. So this is the formula, and in SI units, you know that force is newtons, and area in SI units, it's meters squared. But it's hard to say this each time. So instead of saying Newton per meter squared, you can just say Pascal. So this is the SI unit of pressure, and it's shown by PA. Okay, so we said force per unit area. So for a given force, let's say you have a balloon and you apply some force, the same force, let's call it 5 newtons. And here with the needle, same thing, 5 newtons. But the finger does not pop the balloon. And you know that the needle can pop the balloon. Why is that? Even though we are applying the same force, because the pressure is different in each cases. Here the pressure is more. You have more pressure here. Why? Even though force is the same, but the area, so this is basically the area. So if this is the needle, so this is the area, the cross-sectional area. Maybe it's a couple micrometers. It's even maybe less than millimeter squared. So it's probably micrometer squared. And here it's about centimeters squared. So here the area is less. And if you have less area, that means, so if A is small, and because it's in the denominator, pressure is high. So here there's high pressure. So because of high pressure, the needle pops the balloon. Now, what about the atmospheric pressure? We live in the atmosphere. And because the atmosphere is basically gas, so it applies pressure in every direction on every object. So atmospheric pressure is the pressure of the air around us. It decreases with increasing altitude. So we will see examples. If you go up the mountain, it decreases. At a given altitude, so let's say you're at sea level or somewhere at a given altitude, it pushes an object from all sides. So the pressure pushes an object from all sides. Therefore, it doesn't cause translational movement, but it causes compression. So if you think about this, your hand or your whole body, the pressure, so basically the particles of air, they are hitting your hand from both sides. So they basically impart momentum on your hand. So they give momentum, but the momentum, the impact, it's from these particles, it's to the right, but from these particles, it's to the left. So they cancel out. So your hand is not really, so it doesn't move to the left or right. But what happens is it feels compression. So even though there's no translational movement because of the pressure, because it's in all directions, but it creates compression. So the air compresses your hand a little bit. Now, what is the atmospheric pressure at sea level? At sea level, it's 1.01 10 to the 5th Pascal, or we can write this as 101 kilopascal. Kilo means 1,000, as you know. So you can keep this in mind. So it's about 100 kilopascals. Okay, here's an example. Calculate the force on your palm. So you're going to calculate the force here. Due to the atmospheric pressure, and hand dimensions are, it's about 0.08 meters in this direction, and 0.1 meters, so it's about 10 centimeters in that direction. Not the whole hand, it's actually, we're talking about the palm, this part. So pressure is, we know the pressure, we are calculating force, so we will do pressure times area. The atmospheric pressure at sea level is this number, and we will multiply by the area. So everything is in SI units. So by the way, when you use in the formulas, you don't use 101, you have to use it in pascals, because SI unit is not kilopascal, but it's Pascal, so this value. And if you do the multiplication, you find 810 newtons. So this is approximately the force that an 80 kilogram person applies on any surface. So it's pretty high. You can ask, well, how come our skin or blood pressure can hold this much pressure? Well, our body is designed for it, so it's used to that much of pressure. So there's no problem in the body and the blood temperature. Also, the tissues and everything, the bones, they are already designed for that pressure. So again, same force on both sides. So the hand doesn't move to the left or to the right, but there is definitely pressure, compression on the hand. Okay, so combining all three observations that we see in page 2, so we had 3 observations with the basketball and other things. So if you combine them, what you find is a formula for ideal gas, and it's also called the equation of state. Why is it called the equation of state? Because in a gas, it can be in a certain, it can have certain pressure and temperature values. So it's in a certain state. So the temperature may be different, pressure may be different, also the volume may be different, N may be different. So for specific values of these, it's in a state. So, but it can be in any different states. So, but those states, there are certain, so there's a restriction in the values of these variables, and that restriction comes from this ideal gas formula. So if the pressure is at certain value, volume at certain value, K is already constant, and if N is again at a certain value, so there's only one allowed temperature for the ideal gas, and that would be given by this equation. So here N is the number of molecules in the gas. So if you have, let's say, a vapor, so it will be the water molecule, so they will be H2O. But if you have a noble gas like helium gas, it will be basically free helium atoms, so it will be atoms, but in general, you can just call it molecules in the gas. So basically independent objects. It could be molecules or individual atoms. And K here is called the Boltzmann constant, and its value is 1.38 times 10 to the negative 23rd joules per Kelvin. And T, the temperature, it should be in kelvins as well. Now, what does that ideal gas mean? Why do we call it ideal gas, but not just gas? Well, ideal gas, it's the hypothetical gas model. So in reality, the reality is a little bit different, but this is a good model of reality. So it's a model that is dilute enough. Dilute enough means it's not very dense, so that the gas molecules do not interact with each other. So, so we have the gas molecules, they are moving in random directions with certain different speeds. Some of the gas molecules are not moving at all, maybe they're just stationary. And so if we say they don't interact, they don't collide with each other, then we have the ideal gas, and this is the formula. But if they collide with each other, which happens in reality, in fact, at the room temperature, if you look at the gas in your room, in 1 second, maybe millions of collisions happens, okay? But ideal gas is still good. It's good enough to model the gas in your room, for example. So it's just a model. So it's an idealized model of gas where we assume that the particles do not collide or interact with each other. Okay, so now we can rewrite the same formula if you make these definitions. So now look at this formula. We're going to make some. So N is the number of molecules. If there are 1 million molecules, then you write 1 million here. But we can change the definitions. Let's define Avogadro's number. So it's just some constant number. It doesn't have, so it's just numbers, 6.022 10 to the 23rd. And if we also write, if you also make this definition, where here n is in moles. So let's say you have 1 million particles, so you write 1 million here. And if you divide it by this specific number, what you find is the amount of particles in the container in terms of moles. So for example, if you have in the container, how many, so let's say 6.022 10 to the negative 10 to the 23rd particles you have in the container, let's say. Now, how many moles is it? Well, if you write this number here and divide it by Avogadro's number, which is the same number, then that would mean you have 1 moles of particles. What about if you have 6, so if n is 6.022 10 to the 24th particles, then if you divide it by this number, then there's a factor of 10. In that case, you would have 10 moles. So we are just changing the definitions. And this definition is useful because in a glass of water, how many particles you have? It's not 1 million, it's not 1 trillion, it's actually this huge number, about this huge number. So it's hard to deal with these large numbers. Instead of using the number of particles, it's usually huge. So why don't we just use moles? And that's in fact the case, most of the case in physics and chemistry, people use moles instead of the actual number of particles. So now, so n is, so instead of n here, so instead of n, we are going to write n times Na. So n is moles times Na, and we have kT. Now look at these two numbers. They are already, both of them are constants, right? Na is this number, K is this number. So if they're both constants, why don't we combine them? So if you combine them, then you get another constant, R. And if you just basically multiply these two numbers, so these cancel each other, and you have to multiply these two numbers, and it makes 8.31 joules per mole per Kelvin. So the equation of state for an ideal gas becomes, so instead of Nk, now we have Nr, which is here. So these are both equivalent. You can use either one. But as I said, most of the times you have the number of particles in terms of moles. Most of the times, especially in chemistry, this one is used. Now, what are the units that we have to use in this equation? We have to use SI units. For pressure, it's pascals, not ATM or not PSI. You have to use pascals. For volume, you have to use meter cube. For moles, it's moles. If you are given the particle number, let's say 1 million particle, you have to write 1 million here divided by the Avogadro's number, find the mole, and write it here. R is just this constant, and T temperature should be in kelvins. Now, in most of the problems, it will give you the volume of the container in terms of liters. So you have to do this conversion. 1 liter is 1,000 centimeter cube. And centimeter is 10 to the negative 2 meters. And we also have this cube here. So 3 times negative 2, it will give me 10 to the negative 6. And there's 10 to the positive 3 here. If you multiply them, you will find 10 to the negative 3 meter cube. So this is 1 liter. So 1 meter cube, it's a large thing, right? It's almost like a half of a refrigerator. So 1 meter, 1 meter, and 1 meter dimensions. But 1 liter is 1,000th of this amount. Think about this much water. So 1 liter is actually a small amount of water like this. So if you have a big glass, it's usually half liter. So you can figure out the size of 1 liter. Okay, there's just a warning here. So you have to note that K, for example, here we have K, it means Boltzmann constant. but it may mean in the previous chapter we learned that it also meant thermal conductivity. And in physics 1, we learned that it actually meant spring constant. If you remember Hooke's law, F equals kx. So it may mean many different things. You have to know what it is from the context. So make sure you don't confuse them. Okay, we have an example here. So given that air is 21% oxygen, so in the atmosphere, the air that we breathe, it has only 21% of it is oxygen. So find the number of oxygen molecules in the lungs. So the atmospheric pressure is this one. Of course, in the formula, we have to use 101. So times, we have to multiply by 1,000. So we have to use this value. Temperature is already given. The volume is given, but we have to convert it to meter cube. So it will be 6 times 10 to the negative 3 meter cube. And then we will plug those in this formula. Now, because it says the number of oxygen molecules, it doesn't say it's not asking the mole, but it's asking actually the number. So we have to use the ideal gas equation with the number with uppercase N. So what's asked here is N. So solve for N, it will be PV divided by KT. So atmospheric pressure is here. Volume is converted to meter cube. K is just a constant, Boltzmann constant that you have to look up. And the temperature is 310 kelvins. So 0 degrees Celsius is it's 273 Kelvin. So this one is then it's about 30. So 310 Kelvin. What's the difference? It's about 37 degrees Celsius. Okay, so now this is the air. This is the air molecules, number of air molecules in the lungs, but we want to find the oxygen, which is 25% of it. So we have to multiply this number by the fraction, which is 0.21, which means basically, so 21 divided by 100, 21%. If you do the multiplication, this will be, so you find this, which is the amount of oxygen molecules in the lung given in these conditions. So the air temperature is 37 degrees Celsius, and this is the atmospheric pressure at sea level. So these are realistic values, and this is the number of oxygen molecules. Now the second part, if the person climbs up a mountain where the pressure is less, if you go up, the pressure goes down. How does the number of molecules in the lungs change? Now, the lung volume and the lung temperature are the same. Why? Because, temperature may change a little bit, but you can assume they're the same because it's basically, now this value is actually the body temperature, not the air temperature outside. The outside air may be colder than this, but when you breathe, and when the air stays for a second in your lungs, its temperature raises to this value. So if you go up the mountain, even though the weather may be colder, but still when you breathe, your body temperature will basically heat up the air, so it will come again to this value, the temperature. So then the volume and the T are the same. Okay, so the number of air molecules in the lungs is less due to the decreased pressure at higher altitudes. Now, if you look at here, if the volume is the same and the temperature is the same, K is already a constant, so everything is same except pressure, Now, because the pressure goes down at the high altitudes, then the number of molecules in your lung will actually go down. So basically at high temperature, you have more molecules because the density of the molecules is large. But at high, so I'm going to exaggerate, at high altitudes, you have less molecules like this. So it's less dense, it's dilute. And this is in fact why you have hard time breathing at really, really high altitudes. So again, let's remember, in 1 mole, there are this many numbers, this many molecules. It's actually this long number. So the Avogadro's number is, as we mentioned, it's this number, and its unit, its dimensions, it's basically counting the numbers, but its unit is atoms or molecules per mole. So unit is inverse mole. So now let's talk about these concepts, where one of them is the atomic or molecular mass of an atom. It's shown by uppercase M. So it's the mass in grams of 1 mole of that substance. For example, if you have this many helium atoms, now what would be the weight of those this many atoms of helium? It will be this number. So it's about 4 grams. So the atomic or molecular mass, it's in units of grams per mole, which means in 1 mole of helium, they will weigh approximately 4 grams. What about copper? For copper, it's about 64 grams per mole. And you can also talk about, so these are basically atoms, and we can also talk about molecules. So the hydrogen gas is H2. Hydrogen doesn't, as a gas, it doesn't stay as single hydrogen atoms, but it forms H2. And if you look up from the tables, the molecular mass is about 2 grams per mole. So these values are for the masses in grams for 1 mole. But what about the mass of a single atom? It's shown by lowercase m. See, this is uppercase N, this is lowercase m, which you can find. So these values were for 1 mole, this mini number. So if you divide these numbers by the Avogadro's number, so divide these mass values by Avogadro's number, and you will find the weight of a single atom or molecule. So for example, mass of 1 helium atom. So you take this value divided by the Avogadro's number, and it will be 6.65 10 to the negative 24th grams. And for the copper, it would be this number. So just a reminder, SI units are, so if you ever have to use these values in the formulas, SI units are kilograms, so we have to convert to kilograms, seconds, and meters. Okay, here's an example. So find the masses of an atom of iron and a molecule of nitrogen. Atomic masses are listed in the Appendix E of the book. So if you go to Appendix E, you will find also this periodic table. So it's asking the mass of single atoms and single molecules. So to be able to do that, we will divide the mass numbers. So let me go back 1 slide. So atomic or molecular mass, that was for 1 mole. And where do you get them? Well, you get them from the periodic table. So let's find iron here. So this is iron, and the molecular mass is here, 55.85. So it's this value. And you divide it by the Avogadro's number, so which will give you the weight of a single iron atom in grams or in kilograms. And you do the same thing for nitrogen gas. Now let's find nitrogen, it's here. So 1 mole of nitrogen atoms, its weight is 14.01 grams, but because we're dealing with N2, so we have to multiply this number by 2. That's why we have 28.02 divided by the Avogadro's number, and you will find the weight of a single nitrogen gas molecule. Okay, so there are a couple laws. You can think of them as derived from. They can be derived from the ideal gas law, but historically they were found before this formula. So one of them is the Boyle's law. So basically, it says, after the experiments and observations, Boyle figures out that the pressure varies inversely with volume when N and T are fixed. Historically, Boyle's law, which is this one, it was found before the ideal gas law. So if N and T are fixed, let's fix these. So N is fixed, K, T. So these are fixed. So this is some constant now. PV equals constant. So it's some number, let's say 1 million or 5. Now, and you can experimentally, you can do this. You can fix N and T. So you can have your gas at a, so you can have a piston here. So the volume can change. So this piston can go up and down. Volume can change, pressure can change, but the number of molecules will be fixed because now this is a closed container. And you can also fix temperature by maybe putting this in a heat bath like this. So if you have a certain constant temperature in this liquid, so the temperature here will be always the same. But what can change is P and V. Now, for example, you can change the pressure. So you can, for example, push this piston down. So this would decrease the pressure and decrease the volume, and it will increase the pressure. And if you pull this piston up, so it will increase the pressure and increase the volume and decrease the pressure. So now for different situations, you can write, because this is a constant, you can say P initial, V initial, it's a constant. And if it's the same constant, I can write this for a different situation, P final, V final. So for a gas of N molecules, each curve on a PV plot, so you can see that this is pressure versus volume plot. So there are different curves here, and they correspond to different T values. So depending on the temperature that you want to keep constant, you want to keep this the gas here constant at that temperature T. So it could be different temperatures, of course. It's up to you. But for each temperature, there is one curve like this. So for a fixed temperature, let's say you chose 200 K, then the blue one will be the curve. So what it means is, so on a given isotherm, these are called isotherms, which means iso means identical term temperature. The value of T is the same at all points. So for example, on the blue one, the value of temperature is 200 K kelvins at all points on the blue curve. But what changes is the pressure and volume. For example, at this point, the volume is, let's say, V initial, and the pressure is P initial. But if you, let's say, if you pull the piston up, the volume increases. So now this is the new volume. And this is the final pressure. So what changes is only P and V in this case, because we fixed N and T. So you can use this formula. Basically, find whichever is asked, initial or final values. Or if you know P and V values and also the temperature, you can of course plug those in to calculate the number of molecules. Okay, so here is an example. A cylindrical flask of cross-sectional area A, so this area is A, is fitted with an airtight piston that is free to slide up and down. This is the piston, this dark gray one. Contained within the flask is an ideal gas. There's ideal gas here. Initially, the pressure applied by the piston is 140 kilopascals, and the height of the piston above the base of the flask is 22. So this is 22 centimeters. When additional mass is added, as you can see, there's extra mass is added here. The pressure increases to this value, and assuming the system is always at the temperature 290 kelvins, find the new height of the piston. First of all, you look at here, the number of N, number of molecules is the same, and it's kept at the same temperature. So T is the same. So when you write PV and KT, so these are the same. These are the same. So this part is constant. So then I can use PV initial equals P final, V final. Now, so the pressures are given. So what's asked here is H2, the final height. Now I have to go from the volume to the height. How do you do it? Well, this is a cylinder. The volume is area times H. So in this case, H initial, and the final volume is area times H final. In fact, these areas cancel out. So initial height is 22 centimeters, that's given. So what's unknown is HF or H2, same thing. And you can find it from here, which turns out to be 17 centimeters. Okay, Charles' law is another observation, which is temperature varies linearly with volume. So if you fix the number of molecules and the pressure, then you see that temperature and volume, they are linearly dependent. So how do you fix N and P? Again, if you put your gas in a container where there's no leak, then in this case, N is fixed because the number of molecules doesn't change in the closed container. Now, how do you fix P? So you can heat this gas and the piston is free to move up and down. It can move up and down, but how do you fix P? How do you keep it at the same temperature, same pressure? Well, if you don't touch the piston, which means if you don't push it down or pull it up, then the pressure will be fixed because basically the movable piston ensures that the pressure of the gas inside the container is, so let's call it P I, or just let's call it P gas. It's equal to the atmospheric pressure. So the pressure outside is P AT. So P gas is equal P AT all the time. Why are they equal? Because if they're not equal, then the piston would move up or down until they are equal. And here we ignore the piston's weight. Of course, the piston, if it has a significant amount of weight, it will also contribute to the pressure, but we can ignore it for now. So the bottom line here is if you have a piston that's free to move up or down, and if you do not push it down or pull it up, then it will ensure that the gas pressure inside will always equal to atmospheric pressure outside. Even if you heat it up, you can do different things, but the pressure will be constant. So then this is constant. So N is constant, K is already constant, and you can see here that V and T, they are proportional or linearly dependent, or linearly there's a linear relationship between them. So you can also write this as V divided by T, which is equal to some constant number. Okay, just like we did in the previous slide, we can, from this equation, you can also write VI divided by TI, it's equal to V final divided by T final. Okay, how do I go from here to here? Well, let's say this is 2, the constant number is 2. So if volume is 100, that means T should be 50. Or if I decrease the volume by half, so the volume will be now 50. Now TF should also decrease by half, so it will be 25. Now 100 divided by 50 is 2. 50 divided by 25 is again 2. So whenever you have an equation like this, which is equal to a constant, you can always write an equation like this for initial and final cases. So in the previous slide, Boyle's law, we had temperature fixed, but here we have pressure fixed. So the plot shows here V and T, so the volume and temperature. So before we had pressure and volume, but here the temperature can change, volume can change. We don't have pressure here because it's fixed. So they are linearly dependent. If you have an equation like this, then you have straight lines because of the linear dependence. So here different lines correspond to different pressure values. So they're fixed, but for example, if you add the sea level, this atmospheric pressure will be 100 kilopascals. So then the gas in the container will have the same pressure. So you would use this orange line to figure out how temperature, so the values of the temperatures for different values of volume. But if you go up a mountain, then the pressure may decrease. So in that case, you should use this line. Or if you have a lab environment where you can go to higher pressures, then you would use this one. Okay, now let's move to kinetic theory of gases. Now, all we talked about until now was the thermodynamics, thermodynamical variables like pressure, volume, temperature, but those values are actually the thermodynamics is, so all of those values become a reality because of the movement of the individual molecules. So now the field that relates the individual molecules movements to the thermodynamical quantities like temperature, pressure, that field is called kinetic theory of gases. So it relates microscopic quantities like position, velocity of molecules to macroscopic ones, the thermodynamic variables like pressure and temperature. So pressure is the result of collisions between the gas molecules and the walls of a container. So when we say pressure, it's actually it's basically what makes the pressure. It's the particles are all the time keep colliding with the walls. If you have, let's say, a balloon, now there's always a pressure, right, that keeps the balloon. Otherwise, if there's no pressure inside, or if the inside and outside pressure, let's say it this way, if the inside and outside pressure is the same, then if it's, let's say, if there's a hole, then you would have a balloon like this, popped. But if you have some extra pressure in the gas inside, and so those particles, that means those particles are hitting the walls here more strongly than the particles outside hitting the wall in this way, so that the tension, the surface tension of the ball can be balanced. So here there's more pressure outside, there's less pressure. So more pressure inside, it can balance the pressure outside plus the tension on the balloon, on the plastic of the balloon. So again, basically this happens only because the molecules are hitting the balloon all the time. So basically the pressure is the result of collisions between the gas molecules and the walls of the container. Now, if you remember from physics 1, we talked about impulse, which is the amount of momentum that's transferred from the particle to the wall, and then the wall transfers the momentum back, so the particles bounces back. So when collision happens, two objects, they transfer momentum between each other. So that's not momentum, that's delta momentum, which is the change in momentum. That's also called impulse. And it's related to the force and the time of the force, time of the contact. So the time, it's in maybe microseconds, but there's some time. If you multiply it by the force applied by the wall or the ball, you find impulse. Now you can, if you look at this part of the equation, you can write force as the change in momentum divided by delta t. This is equal to F equals ma, but written in a different way. And delta p is change in momentum, is the initial momentum. So the initially particle had momentum mvx, x in x direction, so mvx. Now after it bounces back, the momentum becomes negative mvx, right? So initially it has mvx momentum, and if it bounces back, the amount is the same, but the direction changed. So it's negative mvx. Now from here, what we have is 2 mvx. Now we're going to divide it by the time for one collision. So time is x divided by v. Okay, so for one full motion, so it's going back and forth. Okay, it's how much, so what is the distance that it goes back and forth? It's 2L, so L times 2. And if you divide it by the speed, you find the time that's required for one full bouncing back and forth. And if you write it here in the denominator, so that's the time. And these two cancel out, and you end up with this value or the variables for the force. So that's the force that's felt by the walls of a particle, of a molecule that bounces back and forth in a container where the length is L, and this is the mass of the particle, and this is the linear speed of the particle or the molecule in the x direction. So how do we calculate pressure now? Well, you have to divide force by area. Now the force, we calculated it here. So the area would be, let's assume the walls, the side lengths are L again. So the area would be, so we have to divide this thing by L squared. And the denominator makes L cubed. So numerator is this value. So we can rewrite L cubed as volume. So this will be the pressure of a single particle moving in one dimension on the walls of a container. So in the next slide, we will generalize this to 3 dimensions. And we will also multiply this by n, because this is just for one particle, but as you know, in a typical container, there are n particles. So we will generalize this in the next slide. Okay, before we move to the 3rd dimension, let's understand the distribution of speed. Now, not all molecules in a gas have the same speed. They don't have the same speed. You can see it here. Some of the molecules are moving really fast and some are slowly. In fact, if you follow some molecules, they sometimes stop, so that they become stationary. But of course, because of the collisions, the speeds are always changing. Now, the speed of the molecules are represented by Maxwell's distribution. And speed distribution depends on the temperature and the mass of the molecule. So, for example, so on the x-axis, we have speed now. So this is a distribution. So the y-axis shows relative probability. It's basically the number, you can think of the number of particles in that given speed. For example, if the temperature is 300 K, so it's about room temperature, you can see that most of the particles, they have speed around, it's about 300, 400 meters per second. But if you raise the temperature to 1100 K, then you can see that the distribution changes. In both cases, there are really, really slow particles, high-speed particles, but this average value or the maximum value, it moves. So for 1100 K, you can see that majority of the particles have speed around 750 meters per second. So if this is the temperature, if you take any particle, it's high probability that the speed of that particle will be around this number. It could be a little bit less, a little bit more, but it's likely that it's going to be, the speed is going to be around this point, because if you, so you can look at most of the particles' speed is around this point, but that doesn't mean that there's no zero speed or low speed particles. There are, and there are also high speed particles, but you can look at the probability of high, or the amount of high speed particles and low speed particles. They are way less than particles that have speed around this value, which is 750. And by the way, these values are realistic. So at room temperature, the particle speed is about 400 meters per second. It's a huge velocity. This is 400 meters in 1 second. But these are because the molecules, they have really, really small mass. They can actually have that much speed for a given kinetic energy. So these are realistic values. Okay, now we have to move to n particles in 3 dimensions, because what we did is one particle in 1 dimension, but we have to move to generalize it to a more realistic situation, which is this. So we start from the pressure of single particles moving in 1 dimension. It was, that's what we did in page 11. So this was pressure from one particle moving only in 1 dimension, x direction. So in a gas, speed is a distribution that we just learned. So replace the speed squared with the average speed squared for single particles. So now, if you remember what I just said in the previous slide, we don't really know the speed of a particle in a gas, but we can say, because the particles, if you have n particles, they will all have different speeds. But because we cannot really account for all the speeds, what we can do is we can use one value, which is the average value. So because I do not know the speed of each particle, and it's really hard to deal with, but instead I can just use the average value of the speed squared. So still single particle, 1 dimensions, but now I replaced this variable with the average. So let's now generalize the results to 3 dimensions. So speed squared in 3 dimensions, if you expand it, you can write it as x, speed of x component of speed squared, average. We are writing averages here for y component and for z component. So if you add them up, well, the averages in each direction will be the same. There's no reason why the average speed in one direction is greater or smaller than the others. So they will be all the same. So instead, for all of these, I can use this one and multiply it by 3. Now, so what I need here, so this is the value which is here. So instead of this value, I can write here v squared. So now I'm moving to 3 dimensions. Instead of only x component, I will write this divided by 3. So send this 3 to the denominator on the other side. So I can replace this value here by this value here, variable. So now write it for n particles. So what you will do is you will just multiply this thing. This was, again, 3 dimensions, but 1 particle. If I multiply by n, then it will be for n particles. So we have n divided by v here. We have 1/3 here. And the rest is m times v average. Now, as you can notice that there's no x here because now we are in 3 dimensions. So this is the pressure, definition of pressure in 3 dimensions for n particles. So we found pressure to be for n particles in a gas in 3 dimensions. So it's this value. Now you can notice that this part looks like kinetic energy, except it's missing 1/2. So I can add 1/2 here. I can add 2 here, so that now we have 2/3 here. And this part, I can call it kinetic energy, average kinetic energy. So, but this is, you can see that there's not n particles here. There's just 1 particle. That's for kinetic energy for 1 particle. So kinetic energy for 1 particle, let me write it here, which is also this value. Now on the other side, I have, so if I leave this part here, so I have to send these guys to the other side next to P. So this term will be 3/2, so basically inverted, V divided by N. So there's P V divided by N. So this is this term. So this term is now equal to 1/2 m v average, v squared average, which is the average kinetic energy of 1 particle. Now, at this point, I can replace it. Remember, use the ideal gas law. Now take n to the numerator here. So then this value is just kT. Okay, so 3/2 kT is equal to kinetic energy of a single particle in a gas. So if someone asks you what is the average kinetic energy of a gas molecule, then the only thing that you have to know is the temperature of that gas. K is already Boltzmann constant, it's a constant number. So it's nice here that if you know temperature of the gas, you can calculate the average kinetic energy of the molecules. But that's just for 1 molecule. Why do we say average? Because we are dealing with averages here. As I mentioned before, it's hard to calculate the speeds. It's actually a distribution. All particles have their different speeds. It's hard to keep track of those different speeds. So what we work with is actually not the speeds themselves, but their average. Now, we can calculate the total. So this was for 1 particle or molecule. Now, how do you go to n particles? Kinetic energy of n particles, it's called internal kinetic energy. It's shown by U. This is not potential energy. This is total kinetic energy of the particles. What I have to do is I have to multiply the single particle kinetic energy by n. N is the number of molecules in the gas. So this was 3/2 kT that we found here. Now I have to multiply by n. So this is the total kinetic energy or internal energy of the gas. Now instead of kT, you can also write instead of uppercase nk, you can write lowercase nr. Why? Because nk is equal to nr. Now, if you remember, r is actually the Avogadro's number times k. And this combination gives us n, because we defined the moles, number of moles is n divided by the Avogadro's number. Now, finally, we can talk about the RMS speed, root mean square speed. This is another kind of average. So root is this root. Mean means average. It's basically another name for average, which is here. And the square is here. So this calculates the average, a type of average speed. So v squared, you can find it from where? You can find it, for example, if you think about this part. So kinetic energy is 1/2 mv squared average, and it's equal to 3/2 kt. Now 2's are gone, so v squared average here is 3kt divided by m. And if you take the square of both sides, then you get this expression. Now, you may ask, why don't we just use V average instead of V RMS? You can also use V average if you can calculate it. In this case, we cannot, but what we can calculate is V RMS. But those, it acts like a V average. Now, the difference is V average will be something like this, but we don't really have access to this variable, because if you look at the calculations, all we have is first take the square and then take the average. But this is really taking the average of V itself, not the square. So because we don't have access to this, we can calculate the closest one, which is VRMS. Why is it close? Because if you look at here, now this is V squared average. Now, V squared average. Now, if I need something like V average, I have to do one more thing here, because this is not in meter per second, this is like meter squared per second squared. So the only thing to get the right dimensions, I have to take the square root of this one. So this becomes something like V average, not exactly, but it's the closest one. And again, why do I use this term? Because that's the thing that appears in my calculations. Okay, here's an example. Find the average kinetic energy of oxygen molecules in air. Assume the air is at temperature 23 degrees centigrade. Now I have to convert it to kelvins. Just add 273. Okay, so this is in kelvins. And I will just use this equation. So K is the Boltzmann constant. And at the temperature here, this is the energy. This is the kinetic energy average of one oxygen molecule, Okay, another example here. The atmosphere is composed primarily of nitrogen, 78%, and oxygen, 21%. Find the RMS speed of oxygen at 293 kelvins. So the molecular mass of oxygen is given. Again, for this one, we will use the formula that we derived. So here it will be, so if you go back to the formula, let's go back it. So we have 3 kt divided by m. So square root 3 kt divided by m. Now, if you remember, m was uppercase M, which is the molecular mass, which we found. We can look up the periodic table, divided by Na. So this becomes 3k Na times T divided by now uppercase M, that we will look up periodic table. Okay, now if you remember, this is R. So that's why we have R here. So either you can use 3 kT divided by lowercase m. This will be the mass of a single molecule, O2 molecule, single, or you can use this equation, this formula, where now instead of K, you have to use R, and instead of lowercase m, you have to use uppercase M. Remember, this uppercase M is the mass of the oxygen molecule, mass of 1 moles of oxygen molecule. So you can use either one. This one you can look up from the periodic table. It's given here, so 32 grams per mole. But if you convert it to kilograms, it becomes 32 times 10 to the negative 3 kilograms per mole. And indeed, that's the number here. So you should go back and forth. You should be able to go back and forth between the variables that include and A, the Avogadro's numbers, or the ones that do not include. Okay, let's talk about these averages again. So this is the distribution of speed. So in this gas, there are some particles with speed 250, some 500, some even 0 maybe. Some have they're really fast, so those particles are here. But if you look at the distribution, so very low speed particles are, their number is low, or their probability of being is low. Also, the high particles are very low. This is like in a typical class like this. If you plot the grades here, let's say these are going to be the students who get F, and these are going to be students who get A. So usually those who get A are, and those who get F are, they are minority, and most of the students are usually here. They get something between C and B. So it's just similar to that curve. Okay, let's go back to the molecules from the students. So here VMP is the most probable speed in the gas, and if you look at the probability, the top point, it's here, and it gives you, in this case, 750 meter per second. So this is the most probable. What it means is if you take a random particle, and the most probable value will be this value, 750. Now, if you calculate VRMS, it will be a little bit higher than that most probable value. These are kind of, this is V average and VRMS. They are averages, different calculations though. So RMS value and average value, they are a little bit larger than the most probable value, because so this part goes to 0, but there's some tail of the distribution here going to further values. So that makes these averages a little bit more than the most probable values. Now, what are the differences between these two averages, VRMS and V average? The average is the average speed. So sum all the speeds and divide it by n. So add all the speeds and divide it by n. You will find the average speed. But in this case, since we do not have access to the speed of each particle, we cannot really write down an equation in terms of pressure, volume, or T. So in this case, it's more like a theoretical thing here. But RMS is, and in fact, this is why we calculated RMS values. It's not exactly equal to the average value, but it's very close. It's very close to the average. So since we cannot calculate the average speed, we can calculate the RMS, which is calculated by V squared, take first the square and the average. Of course, we do not record the speeds of each particle and do this calculation, this averaging, but we relate this average to the thermodynamic variables. In this case, it's the temperature. So instead of recording, measuring, or even if you can calculating the values or simulating the values of speeds, instead of that, you can just use the temperature to calculate the average. So this is something that, so what we do here is we are using a macroscopic value, quantity, temperature from thermodynamics, and we use it to calculate a microscopic quantity, which is the RMS average or RMS speed of the particles. Okay, so now let's move to solids and elastic deformation. There's not much, there's no really thermodynamics in this section, but this is also important. Solids not only expand or contract with heat that we learned in the previous chapter. So if you change the temperature, if you give some temperature to a solid and change it heat and change its temperature, this was the initial length. If you remember the Eiffel Tower, initial length of the object, and this value, it depended on it's some numerical value, and it depended on the type of the particle. It was different, the type of the object. It was different for iron, different for other objects, and from here you would calculate the change in length of that object. So that was from it was from chapter 16. So, but solids not only expand or contract with heat, they also do so. So they expand or contract under the effect of applied force. So if you pull this iron, or any other object, then what will happen is now this solid, if you look at it really from the if you think of its microscopic structure, it's basically a crystal. It has, if this is iron, it has iron atoms like this. And if you apply force, well, of course, these atoms, they attract each other. But if you apply force, you can move those atoms to other places. So what happens is the new crystal becomes more like this. So there's more distance between the atoms. And you can do it by an applied force. Now, the relation or the formula that relates the extension, the amount of extension, the initial length, the cross-sectional area, and the force is this relation. Here, this is called, Y is called Young modulus, and it quantifies the amount of deformation. So here's a table for Young modulus for various materials. For tungsten and steel, it's really, really high. But if you go to, for example, bone or nylon, it's a smaller value. So for a given L0, A, and F, let's say F is fixed, L0 is fixed, and A is fixed. So you are going to use this object and you're going to apply it to a given force, fixed force. Now, for different materials, you can think of now this small Young modulus leads to large extension. If this, so F is constant, L0 is constant, A is constant. If Y is small, so in that case, if Y is small, then the extension will be large because these are inversely proportional. So under the same force, nylon changes its length the most, and tungsten and steel change their length the least. Why? Because if Y value, Young modulus, is small, then the deformation amount becomes maximum. Now, if you look at nylon and the bone, They're the smallest in this table, and tungsten and steel, they're the highest. And we know that nylon actually, it deforms more than the steel. So some materials also may have slightly different Young modulus values for stretching and compression. So for stretching and compression, bone, for example, it has slightly different values. For tension, which means stretching, so it's just like here, pulling it, it's 1.6 10 to the 10th. But for compression, it's a lesser value, 0.94 10 to the 10th. So in this example, what we have is a person carrying a duffel bag. At the local airport, a person carries a 21 kilogram duffel bag in one hand, assuming the humerus, the upper arm bone here, supports the entire weight of the bag. Determine the amount by which the bone stretches. The humerus may be assumed to be 33 centimeters in length and to have an effective cross-sectional area 5.2 10 to the negative 4 meter squared. So area is given. So this is L0. And force, we can find the force because the force on this bone will be basically the weight of the bag. So 21 times the gravity of Earth, which is 210 newtons. Now, so we know force, we know L0 given, and we know Young modulus from the table. Now, this is stretching. So let's go back to the table. So I have to use the tension, not the compression, but tension. So 1.6 10 to the 10th. And in fact, for Young modulus, it's used here. And area is given, so everything is given. I can calculate the extension. So it's this amount. It's about 10 micrometers. So this amount of extension it's really small. It's comparable to the diameter of a hair, but still there's some extension. Okay, so we talked about extensions and compressions in one dimension. Now we talk about here the shear deformations. That's the second type. Shear deformations changes the shape of the solid. So in this case, you don't pull it up or down, but you push it on the surface. So the force, so if you remember in the previous case, we had this metal or any other material, it doesn't have to be metal. So this was the area, and we pulled it in the direction that's perpendicular with the force. So the force was perpendicular to the area. But here the force is on that plane, in the same plane. So when you push any object, it doesn't have to be a book like this. Any solid, if you push it this way, it will deform. So it will go like this. It will be more like this. Okay, so different materials deform differently for a given force. So shear modulus S quantifies the amount of deformations. Again, we have it. The shear values of tungsten and steel is large in comparison to the shear modulus value of lead. So for a given L0, now in this case, L0 is here, the height. Okay, it's not the length. And area is the area where the force is applied. So if you fix L0, A, and force, so for given values of these, now if shear modulus is small, then you get more deformations. So in this case, lead has the least in this table, shear modulus, then it will deform the most. But if you look at tungsten and steel, because their shear modulus is large, then their deformation will be smaller. So again, this L0 is thickness, this thickness, it's not the length. Okay, finally, so we talked about extension or compression in one dimension. We talked about shear deformations. Now the third kind of deformation is the bulk deformation. Pressure applied in all directions changes the volume of a solid. Now this is volume changing deformation. So, and in this case, bulk, the constant we have is bulk modulus. It's shown by B. It quantifies the volume change. So you apply some pressure. So you change the pressure, increase in pressure here. And of course, the volume changes. So the initial volume is this one. Okay, this is V0. So this and this one is the final volume. This one is the initial volume. And the change of volume is delta V is this part. So you have to calculate this part. If this is spherical like this, to calculate V final delta V, you would write 4/3 pi, let's say R initial, which is this is the, R final, minus, well, we have cubed, 4/3 pi R initial cubed. So this is how we calculate the change of volume. So when pressure is increased, final minus initial. So the final is larger, initial is smaller because you are increasing the pressure here. So this value becomes, it's going to be positive because you're subtracting a small number from a large number. But because the volume will decrease, now the final volume is less. Like if it's 5, initial volume was more, let's say like 7. So this is a negative number. So it will be negative. So to compensate the sign difference, we have a negative sign in the equation. So this negative sign is there because of the signs of delta P, the sign difference between delta P and delta V. Okay, so stress and strain, these you will see these terms also in the literature. So we refer to the force per area, which is basically pressure, as stress. If it's perpendicular, it's pressure, but if it's in the same direction or if it's in the plane of the surface, then it becomes shear. But the general term for them is stress. And the amount of resulting deformation is the strain. So the strain can be in one dimension, delta L. If there's shear, then it's called, it's shown by delta X. Or if it's a bulk deformation, as we saw in the previous slide, then it's delta V. So these are the strains or the amounts of deformations. Now let's go back to the one-dimensional case. If you remember, the formula was this, and Y was the Young modulus. Now, if you combine these three terms, then actually what spring constant is. Now here, K is the spring constant. Remember from physics 1. Now if you rewrite it, it's K times delta L, and instead of delta L, we used in Hooke's law, Kx. So this is basically if you have a spring, let's say this is the equilibrium point, this is the equilibrium point, and let's say you stretch it to this point. This is x equals 0 and this is x. So if you stretch or compress it for the amount of x, the force will be, so the force, there will be a restoring force in the opposite direction of extension or compression. So that force is given by the spring constant times the amount of deformation or extension or compression. So we use this in physics 1 a lot, and now you know that K is actually, it depends on the materials itself. So the Young modulus depends on the material. It depends on the length of the spring, and it depends on the area of the spring. So it's K is a combination of these three variables. Now, F equals Ka, it's a linear equation, right? If I stress F, if I plot stress versus strain in one-dimensional case, it's X. This equation is linear. So this is, if it's linear, it's the Hooke's law. Stress is proportional to strain. F is proportional to X. That's the regime where Hooke's law is valid. Now, if the stress is beyond the linear regime, the linear Hooke's law does not apply anymore. So you increase, so you extend the spring, stretch it, and at some point, after some point, if you do this experiment, you will see that the linear relationship is lost. So it becomes not linear anymore. So there's a deviation from Hooke's law. And if so, after a certain point, there's a certain point, and after that, if the stress is even more than that value, then it leads to permanent deformation as seen here. So this is called elastic limit. If you extend it beyond, if you apply force, or if you extend it beyond that value, maybe 5 centimeters, maybe 10 centimeters, then you basically deform the spring and it cannot recover back to its equilibrium point. So this is a permanent deformation. Okay, now we move to next section, where we go back to thermodynamics, and we will talk about phase equilibrium and evaporation. So if you have, let's say you have a container like this, and initially this part is vacuum, which means empty, and there's liquid here. Now, if you have a liquid, if it's not at 0 Kelvin, it has, the molecules are moving, right? Because even if if you have water at 0 degrees Celsius, so 0 degrees Celsius means 273 Kelvin. So when there's temperature in Kelvin, that means there's kinetic energy. So that means all these water molecules are actually moving in all directions. Of course, there's going to be a distribution in the speed. There's not just one speed. All particles, they have their own speed. It's a distribution, but the point here is they are moving. So now, because in the distribution, the sum of the particles at the tail, they have really, really high velocity, which is higher than the average point, average speed. Now, those can actually escape the liquid and go to this empty area. So high-speed molecules escape the liquid. So this continues, and then after some point, when, of course, these molecules here, the gas molecules now, they can go back into the liquid. This also happens. Now, initially, it's mostly in this direction, from the liquid to this empty room, or the vacuum part. Of course, when the density of gas here increases, at some point, the amount of particles that escape from the liquid to this part here will be equal to the amount of particles, or the rate of particles, gas particles, going back into the liquid. So when this equilibrium is reached, and that's called equilibrium, so molecules leaving and entering the liquid are in balance, so the rate is in balance. So in that case, we have equilibrium vapor pressure. So whenever you have a liquid in a container, there is always some gas at the top of that liquid. So this process continues until the gas is dense enough. Gas here is dense enough that the number of molecules returning to the liquid equals the number of entering the gas. So there's a constant flow of molecules in both directions. That's what I explained here. But when the phase equilibrium is reached, that's the third case here, the number of molecules in each phase remains constant. So the numbers Still there, some go in, some go out, but these rates are equal when the equilibrium is reached, or we can say the other way around, when these rates become equal, going in and going out of liquid. When the rates are equal, then we reach equilibrium. So phase equilibrium is reached. Why do we call it phase equilibrium? Because we have two phases, liquid and gas in this case. So those two phases are in equilibrium. The pressure of gas when equilibrium is established is referred to as the equilibrium vapor pressure. Okay, so now let's discuss the difference between evaporation and boiling. So what I described in the previous slide, it was evaporation. So we had some liquid here, its level is somewhere here. There are some really high-speed particles which can escape from the liquid. Also, if you have gas particles here, it's also possible they can go back in. And when the rate is the same, then we get the equilibrium between the phases. So evaporation is basically faster molecules escaping the liquid, and it happens at all temperatures. So even for water at 0 degrees, there's going to be some molecules which have enough speed to escape the liquid, even if it's 0 degrees Celsius. Now, boiling is something different. So, by the way, if you have a container like this, it could be a vacuum here, or it could be atmospheric pressure. So, in this case, the evaporation happens because air pressure is larger than vapor pressure. So it doesn't boil because the air pressure is larger than the vapor pressure. So you can think of this way, the air pressure is so high that it cannot, even though some particles can escape, still most of the liquid is here. So the air pressure is pushing the liquid, so preventing it to boil. But if the air pressure is equal to vapor pressure, remember vapor pressure is coming from this liquid. When it's equal or smaller, air pressure is now not enough to keep the particles, so the particles can go up. In fact, you can see here the gas bubbles form, so this is actually boiling. So boiling happens when the air pressure above the liquid is not strong enough and bubbles form in liquid and raise to the surface. Now this is actually not strange if you don't have any or enough pressure down, because these particles, they have already moving in all directions because they have kinetic energy. Now there's no reason why they should stay at this level, right? If there's not enough pressure, so they will actually go up, the bubbles will form, they will push each other, so they will go up, so there will be boiling. Okay, so when the vapor pressure of a liquid is equal to the atmospheric pressure, boiling starts. That's something we said. At the sea level, remember, vapor pressure is coming from the liquid itself. So if it's a water, so there's water here, then the particles that escape water, so H2O, they form the vapor pressure. But in addition to this vapor pressure, of course, there's also the atmospheric pressure. So both of them. So boiling starts when they are equal. At the sea level, atmospheric pressure is about 100 kilopascals. So water boils at the sea level. So if water boils so this is the atmospheric pressure. Remember, the boiling happens when the vapor pressure equals the atmospheric pressure. So I have the water pressure curve for water here. So here we have the pressure in kilopascals and we have the temperature. Now, at the sea level, for water to boil, we need its pressure to be equal to atmospheric pressure, which is here. So what is the temperature that satisfies this? And that temperature is 100 degrees Celsius. But what happens if you climb up the mountain? At the mountaintop, let's say 10,000 feet, the pressure drops to 70 kilopascals. So from 100 at the sea level, it drops to 70 kilopascals. So now the pressure at the mountaintop, it's here, 70. So at 70 kilopascals, what is the temperature for water? It's about 90 degrees. So water will boil around 90 degrees. Remember, there's not enough air pressure to keep the water down in the cup, in the container. So that pressure is lower, so the water can boil at a lower temperature, which is 90 degrees Celsius. So it may be, is it good? Well, it's, if you're cooking, it may not be good. It may be harder to cook at high temperature, high altitudes. Should be altitudes. Since the water will boil at a lower temperature, and you can't increase water temperature once it started boiling. So if you have some sort of food that needs to be cooked at high temperature, let's say about 100 degrees Celsius, but you can only go up to 90 if you're at the mountaintop. Why? Because once it's boiled, it turns into steam, right? Water turns into steam. You cannot really increase its temperature anymore beyond 90 degrees Celsius. So the other thing that I can tell you is that it's interesting that you can boil water even at 0 degrees Celsius if you can reduce the pressure sufficiently in the lab in a vacuum chamber. So you have the cup here, you have the water, so that normally there's air pressure, but if you close this and suck out all the air pressure, what happens? Now, the pressure goes down, the pressure goes down. In fact, it goes all the way to here. So the boiling temperature, if you look at the curve, it goes from 20, 10, and it may go all the way to 0. So water boils at 100 degrees is a special case. It only happens at the atmospheric pressure at sea level, which is 100 kilopascals, but at other pressures, water boils at lower or higher temperatures, lower or higher than 100. Now, this takes us to the subject of pressure cookers. So if pressure is high, let's say the pressure is, let's say this value. It's twice as large as the atmospheric pressure. Of course, you cannot get to this pressure in an open pan. You have to have a closed pan, sealed. But if you can reach to this pressure, 200, then the water will boil at 120, not 100. Is it good? Yes, because by that way, you can increase the water temperature to higher temperatures. What happens if I open the lid? Well, if I open the lid, the water will boil at the atmospheric pressure, which is 100 degrees. But 100 degrees is lower than 120. And if once it boils, I cannot increase the temperature anymore. So it will stay at 100. But if I wanted to raise it to 120, because after 100, it starts turning into from liquid phase to gas phase, right? So it becomes a gas. But if I close the lid, then I can boil it because the temperature, the pressure will be high. I can raise the temperature, the water temperature, to even further to 120. So if pressure is high, water will boil at a temperature higher than 100 degrees Celsius. If the pressure cooker is in the pressure cooker, food is cooked at a higher temperature, about 120 degrees Celsius. And this is the reason why food cooks faster. So it cooks faster and better at high temperatures, especially if you are cooking meat. Okay, let's also talk about phase diagrams. So in the phase diagrams, we have pressure here and we have temperature here. So there are different phases. So this phase is solid phase. So if we are talking about so for the case of water, it will be ice. For other materials, it will be the solid form of them, solid phase. Here we have gas phase, and here we have the fluid phase. Now, so this transition is, everybody knows this, it's liquid to solid phase transition. So for a given pressure, let's say the pressure is this value, if you increase the temperature from here to this value, what happens if you increase the temperature? The solid basically melts. So this is melting this direction. And if you decrease the temperature of a liquid, then it solidifies, so it becomes a solid. This curve is called fusion curve. So it separates this line, it separates solid phase and the liquid phase. And we have another curve here. It separates the solid phase and the gas phase. So here it's gas, here it's solid. So it's possible that if you to turn a solid into gas directly without going into the liquid phase, and it happens at low pressures. So you should be able to have a low pressure, maybe use vacuum chamber. So if the pressure is below this value, okay, so let's say this value. So anytime that you increase the temperature from here, let's say from here to here, so if the temperature increases, you go from solid phase to directly into gas phase. So this is possible. Or let's say we have at a low temperature enough, let's say the temperature here, what you can do is if you have a gas, so this is gas phase here, if you increase the pressure and go to this point, so at a given temperature, low temperature, by just increasing the pressure, you can go from gas phase to the solid phase, or if you decrease the pressure, you can go from solid phase to gas phase. That's also possible. And this curve, it separates the liquid phase and the gas phase. Fluid here, I will come to it. It means liquid. It's a general term for liquid and gas. It's a general term. So this curve separates liquid and gas. So for a given temperature, you can change the pressure to go between liquid phase and gas phase. If you increase the pressure, of course, gas condenses, turns into a liquid, or you can go the other way around. Or for a given pressure, let's say this pressure, you can change the temperature to go between the liquid phase and gas phase. For example, for water, if you heat it up enough, it will turn into steam or water vapor. Now this line ends at this critical point. So what happens after this point? Let's say, what is the phase at this point? So pressure is this value. The temperature is that high temperature value, specific values. So here it's in between. So it's not exactly like liquid here, not exactly like gas, but it's kind of it's a strange form, which is a combination of liquid and vapor, liquid and gas. And there's one more point that's interesting. It's the triple point. So before the triple point, maybe we can talk about what happens exactly on this fusion curve. Well, on this fusion curve, you have water and ice together. So they're at the same temperature. So you have both water and ice at the same temperature. So here on this curve, you have gas and liquid at the same temperature. An example is, let's say you have a closed container. Maybe you have your coffee mug and its lid is closed. So you have some water or coffee here, and it will have some gas here. So, and they're in phase equilibrium. So that would correspond to a temperature and pressure values on this curve. And there's another point where the three curves meet. So that's called triple point. And if you can, but this is very specific value. You can see that it has a certain temperature, specific temperature, and very specific pressure. So these curves, you can be on these curves at different pressure and temperature values, but this one is just one specific temperature and pressure value. So if you can get to exactly this point, which you can do in a lab, and that's the triple point, you can have all three phases together. For example, you can look up YouTube videos on YouTube. You will find some experiments where you have the water. So in the cup you have ice. You have at the same time liquid, and it's boiling. So it produces gas. So all three phases, you can have them at the same time if you are exactly at the triple point. Okay, so this is the phase diagram of almost all materials. They have a phase diagram like this for solid, liquid, and gas phases, but water's is just a little bit different. This curve in water is more like this, and you will see in the next slide. Okay, so for most materials, again, that curve that separates the solids from liquid, it goes like this. But water is different. Now, increasing pressure from A to B. So let's consider first most materials. If you increase the pressure of a liquid, increase the pressure, it will turn into solid. But in the case of water, if you increase solid, so this is going to be ice. If you increase the pressure on ice, it will actually melt. So increase the pressure, so you find liquid, which is water in liquid form. But for most materials, when you increase the pressure, when you squeeze them, they don't melt. They actually solidify more. But water is, it's different. It's really particular to water. If you have ice, and if you put pressure on it, and you can actually try water and try to put some pressure with some knife on the ice, and you will see that the knife, even though it's a cold knife, just because of the pressure, it will melt the ice a little bit on where the contact between the ice and the knife is. And this is actually what makes ice skating possible. Because if water was just like most materials, the ice, the blades of the skates, the blades are like this. So they are actually putting pressure on the material. If it was just like most materials, it would not melt. But because it's water, because when you increase the pressure, ice turns into water, so it melts. Not by the temperature, it's the same temperature. But what melts it is just the pressure. So ice skates, the blades, apply high pressure because the person is wearing them, and they melt the ice. So they momentarily melt the ice. So momentarily you have some water, a film of water. It's thin, but it's enough for you to slide. So ice skates glide actually on the thin film of water, not ice. So when you see someone is gliding with ice skates, they're actually not touching the ice, they're actually touching the water here. And because water is liquid, so that makes the person to glide on that water. Of course, when the person goes away, the water melted, it freezes again because there is a huge amount of ice below it. So that water is only produced momentarily, but that's enough for skating. Okay, now let's talk about sweating. Sweating cools us off. So we have, in this picture, we have, so that this part is skin, our skin. And when we sweat, we get our sweat glands, they produce this drop of liquid, water, mostly water. So this is the, let's say this is the sweat drop. So if it's, so probably you have experienced this, if you, so at hot temperatures, you sweat, but if there's no breeze or no wind, that sweating doesn't cool you off. So sweating itself is not enough. You also need some wind, or even, even if a little breeze, that's fine, but you need some air movement. So what happens? First, the wind creates low pressure. If there's wind, the pressure here drops. This goes back to the Bernoulli's laws. So the pressure drops here. Now what happens if the pressure drops? Low pressure means easier evaporation. Remember, the pressure is the one that keeps the particles here, not so that they can't boil. And if the pressure is low, then you will get more and more particles that escape out. But who's going to escape first? Not the slow particles, but the fast particles. So fast, which are the energetic, high energy particles in water, escape. So the temperature of the sweat drop decreases. So this has certain temperature because of the kinetic energy of the particles. But if you lose the high speed particles, high kinetic energy particles, the energy goes down, so the temperature goes down. Now, next, when sweat becomes cooler than the skin, initially they were at the same temperature, now sweat has less temperature, it draws heat from the hotter skin. So some heat will be drawn from the skin. So that will make the skin cooler. So dogs, should be dogs. Dogs don't have sweat glands. So what they do to cool off, they take out their tongue. As you can see here, they take out their tongue and pant. Panting is basically breathing quickly. So the reason that they do it is because they cannot sweat. They don't have sweat glands on their body, so they can only sweat or lose energy, lose heat through their tongue. So they open their mouth and they pant, so that at hot temperatures, so that they can they can cool off. Okay, now we move to the next section, which is about latent heats. The word latent, it means concealed or hidden, like hidden energy stored in a compressed spring. Here, the energy is stored. It's latent in a sense that you don't really see. It's not like kinetic energy. Kinetic energy, you see particles moving. As I showed you in the animations, you can say easily that there's some energy right there because they're already moving. Here, there's really no movement, but there is still energy stored. That's why it's called latent. It's kind of concealed or hidden. Latent energy in matter is the intermolecular bond energy in liquids and solids, which keeps the molecules close to each other. If you think about a water, for example, in a cup, the water molecules are not completely turning into gas all of a sudden because each H2O, so this is one of them, so one H here, so this is water molecule. So all of these water molecules, they have oxygen, hydrogen, hydrogen. So these hydrogens, they are attracted to other molecules. So they bond hydrogen bonds. So there are some bonds between molecules. In the case of ice, of course, it's already solid. There are also attractions between the bonds. So the chemical bond energy is basically it's the latent energy. At the phase transition point, so at the atmospheric pressure for like ice at 0 degrees or water at 100 degrees Celsius, giving heat to the system does not raise the temperature. So let's say you have ice at 0 temperature, you start, so let's read the rest. Giving heat to the system does not raise the temperature, but it changes the phase. So let's say I have ice at 0 degrees here, point A. Now, if I give heat to that ice, its temperature will not raise because first it has to go from ice to water. So first it has to melt. So at phase transition points, 0 degrees, and also at 100 degrees. So you have water, and water comes to 100 degrees. And after that point, even if I add energy, add heat to the system, the water temperature will not raise like this. It's not going to happen because now the energy will go into the phase transition, so the water will turn into steam. But that happens at the phase transitions. Of course, if you have water at, let's say, 60 degrees, if you give heat to water, you will increase its temperature, which is shown by the y-axis. So this is when the kinetic energy or temperature of the molecules does not change. So here, for example, during melting, the kinetic energy of the molecules does not change. Remember, kinetic energy is related to temperature. But what changes is the latent hidden energy in the molecular bonds are being broken. So you have ice, you have the crystal structure like this, maybe. So each of them are, let's say, H2O molecules, but they're in the ice, they're in this crystal structure like this. Okay, if you give heat, you don't, so that heat is not going to into the molecules to increase their kinetic energy or temperature. It goes into the bonds during this, but during this phase transition, that heat goes into the bonds and it breaks the bonds. Okay, what happens when you break the bonds? Well, there will be in the liquid phase, so ice goes to water. So there will be still some bonds, weaker bonds. But as you can see now, the crystal structure is broken. So we actually broke some of the bonds, even though there are now some weak bonds. But that energy that we gave, it went into not kinetic energy, it went into the breaking the chemical bonds. And because it did not go into the kinetic energy, during the phase transitions, you can see here, the temperature does not rise. But if you're here, let's say, whenever you give energy, heat, then that heat will go to the molecules, so their kinetic energy and speed will increase, so the temperature will increase. So you can increase the temperature of ice. Let's say you have ice. Ice doesn't mean it's always at 0 degrees. You can have ice at negative 20 degrees Celsius. This is in degrees Celsius, not Kelvin. So if you give ice and heat, then you will raise its temperature to 0 degrees. Now at this point, after this point, you can see that this is heat added in the x-axis. The heat added will go into breaking the molecular bonds, so there's going to be some melting, which is phase transition. Now, after it completely turns into water, the heat that you give it, it will go to the kinetic energy of the particles where the temperature increases, because remember, they are related. Now, when you have water at 100 degrees, after this point, you keep giving it energy. Now, this is going to be phase transition from liquid to gas. So the water will turn. So now at this point, you start to break the bonds, the weak hydrogen bonds between the water molecules. So you are breaking. So this is oxygen. This is 2 hydrogen. Okay. So you're not breaking these bonds. Otherwise, you will get hydrogen gas and oxygen gas. But what you're breaking is there's some weak bonds between different water molecules. So this is oxygen. Okay. So you don't break the water, but you are breaking these bonds between different water molecules. So now what you get is, of course, gas. So you're turning it into gas. Okay, at 100 degrees. So once you have gas, water vapor, or steam at 100 degrees, and if it doesn't go away, if it's in a closed container, then after this point you can increase its temperature. So you can have, let's say, steam at 200 degrees if you continue giving energy or heat to it. Okay, so the heat required to convert 1 kilogram of matter from solid to liquid is called the latent heat of fusion. Fusion here, instead of fusion, you can think of it as melting. It's shown by F for fusion. And to convert from liquid to gas, it's called latent heat of vaporization. And it's shown by LV. So here's a table. So if you are converting solid to liquid, so ice to water, then you have to use this value. But if you're converting from water to gas, which is vapor, or vapor to water, doesn't matter. So if it's a liquid gas phase transition, then you have to use this value. If you're dealing with oxygen, gold, or benzene, or any other material, depending on the phase transition, if it's melting, you use this column. If it's vaporization or condensation, like going from gas to liquid, then you would use this column. So you find for the material, you find the value, and you multiply it by, so L value latent heat, either for this one or for this one, and you multiply by the amount of material, and you will find the heat that's required for to change the phase transition. Now, as you can see, there's no temperature here. So as you can remember from the previous slide, during the phase transitions, which is the phase transition happened here and also here, and you can see from the plot, the temperature does not change during the phase transition. So that's why we don't have temperature in this formula. So again, this is the amount of heat that's required, or energy, to change the phase of a material of mass m. And the latent heat value, you have to look up the tables. So Q is it's in joules actually, because it's energy. Now L, the latent heat, is in units of joules divided by kilogram. Okay, so Now, in this example, we have, so the question is, what is the total heat required to take 0.55 kilogram ice at negative 20 degrees Celsius to positive 30 degrees Celsius? So in these problems, it may be a good idea to plot this graph. So you start with ice at negative 20 degrees. So here it's negative 20 degrees. And then you want to get it to 30 degrees. So let's maybe do this. So this is 30. So you want to get it to 30 degrees here. Okay, how much energy would you spend for, so how much heat do you have to give to the system? So first you have to take the ice at negative 20 degrees Celsius and get it to ice at 0 degrees. Now here, as you can see, you are changing the temperature. So when you change the temperature, you use this equation. We learned this equation in chapter 16. So this is the heat required for this mass of ice to raise its temperature from negative 20 to 0. So the final temperature is 0. So this is delta T. Final is 0. Initial is negative 20. So the change is 20, which is here. You have to look up the specific heat of ice. It's 2090. And the mass is given in the problem as 0.55 kilograms. So because we used SI units, and you find the answer in terms of joules. So this is the amount of joules. Now what we have is, we have at this point, we have ice at 0 degrees, ice at 0 degrees Celsius. Now we have to get this ice at 0 degrees Celsius to water at 0 degrees Celsius. Okay, now because this is a phase transition, the temperature will not change, because you can see temperature is at the same level, which is 0. For phase transitions, I use the formula which doesn't have delta T. So for fusion or melting, I have to look up the table. For water, it's this value, and just multiply by mass of water here, or ice, and you will find this much heat is needed to get the ice at 0 temperature to water at 0 temperature, 0 degrees Celsius. After this point, I have to take this water at 0 degrees Celsius and take it to this point, water at 30 degrees Celsius. Now, because there's temperature increase here, I have to use this formula from chapter 16. Now, specific heat of water, you have to again look it up. And notice that it's different. Specific heat of water is different than the specific heat of ice. So there are different numbers, even though it's the same material. But for different phases, you have different numbers. So if you do this calculation, delta T should be 30, because you're going from 0 to 30. And this is the amount of heat that you have to provide to the system. Now, the total heat required is actually the addition of all of these. So if you add them up, this is the amount of heat that you have to give to the system to take it from negative 20 to 30 degrees Celsius. Okay, so in phase changes, heat flows from hotter object to colder object, and the energy is conserved in these processes. So let's say you put a ice at negative 10 degrees Celsius to a water at 0 degrees Celsius. Now so the water is hot in this case, ice is cold. What will happen? The heat will go from water to the ice. Okay, so the heat Q that leaves the water, it goes into ice, and it will turn a sum of, so it will actually raise, in this case, it will raise the temperature of the ice. So in this case, it goes from -10 to 0. Of course, if it's not always possible, so it depends on the mass of the water, because you need to have enough mass of water to be able to provide that much energy. And as you remember, in all Q formulas, there's always mass here in other terms. So, and then what happens is, now, because some of the heat at 0 degrees, so this water was at 0 degrees, it lost some of its heat to this ice to raise its temperature from -10 to 0. Now, what happens if you take some energy from water at 0 degrees? Let's go back to this plot. So you have water at 0 degrees. What happens if you decrease energy? So this is the energy added, so I have to go to the left direction. If you decrease energy, then you turn water at 0 degrees. In fact, actually it's here. This point is ice, completely ice. This point is water, but they're all at 0 degrees. So if you decrease the energy, if you take out energy from water, its energy will go down. So we have to move to the left. So you will create some ice. So at this point, you have some water and some ice. So let's go back to this figure. So I had water at 0 degrees. If I take energy from that water, some of that water will turn into ice. In fact, you can see it here. So this part was actually water, but because it gave energy to the ice, now that went, this part of the water, initially it was water, its temperature went below 0, so it solidified, so it became ice. But the point here is the energy is conserved in these processes. So the water lost energy or heat, but it went into the ice. So before we had ice at -10 degrees Celsius, but now we have ice at 0 degrees Celsius. Now, this is an application of the energy conservation. So in this example, what we have is we have an initial mixture of 3.95 kilogram of lemonade, which we can think of as water, which is here. It's at 20 degrees. And you add some ice at 0 degrees. And the amount of ice is 0.045 kilograms. What will be the final temperature after they reach equilibrium? Now, first of all, final temperature for both will be the same, right? Maybe so in this case, the water amount is large, it's almost 4 kilograms, and the ice amount is really, really small. So this water, we can say, and water is at 20 degrees, this water is certainly will melt the energy, the heat from the water. It will go into the ice and it will melt it completely. So at the end, we will have some mixture, not a mixture, it's completely water. And the temperature, the final temperature will be something between 0 and 20. So let's calculate that final temperature. So first, heat needed to get ice at 0 degrees to water at 0 degrees. So what is the heat that's needed to melt this? So for melting, we use fusion. So you multiply the mass of ice and L fusion, latent heat value for melting transition. And you look up the table. and you find this much energy is needed to melt this ice. Now, this heat will come from water at 20 degrees. So we have the water's mass and what will be the water's final temperature after giving heat to the ice to melt it. Well, we can calculate it from here, mc delta T. I put delta T in within the absolute value because the final is actually lower than the initial in this case. So we would get a negative sign, but we don't have to care about it at this point. So this is the energy that's used, that's given by the water to the ice. So we are using it on the left-hand side. And if water gives out that much energy, what happens at its final temperature? The initial was 20. If we calculate it from here, the final water temperature becomes 19.1 degrees Celsius. Are we done? Not yet, because what we have now, water. So we have water at 19.1 degrees Celsius. Okay, so the lemonade, and we have some part of that water, which is ice, ice melted, if you remember, and that's water at 0 degrees Celsius. So that's the melted ice. Now it's water, but it's at 0 degrees. The lemonade itself is 19.1 degrees. So now we have to, so that's water at 0 degrees will draw more energy now, more energy from the water so that they can come to the equilibrium. Now let's calculate it. So the heat lost by water here, the lemonade, will be gained by the cold water. So if you add them up, because energy is conserved, it will add up to 0. Why? Because one of them is going to be negative, the other one is going to be positive. So for the first term, you're using, so this is the mass of the lemonade, which is 3.95. So seawater is this value. Now, both of these, the 0 degrees, water at 0 degrees, and water, lemonade at 19.1 degrees, they will meet at a common temperature. So both, the final temperature of both will be the same. So I'm going to call it T final common. And so the hot water, it's initially at 19.1, which we calculated here. And for the cold water, its mass is small. It's given here. The C value is the same because both are now water. Now, the final common is, we don't know the final temperature, but it's the same. So the point here is I'm using the same T final. And the cold water was initially at 0 degrees. Now, if you solve this equation, you will find they will meet the equilibrium temperature will be 18.9 degrees Celsius. And it's indeed between 0 and 20. Okay, this is the end of this lecture. See you in the future videos.